Okay, welcome to everyone for our seminar about industrial air cleaning. So we are from the Reven company. Reven stands for Rentschler, the family name of our founder from 1905. And Sven stands for ventilation. We are with the manufacturing Stuttgart area in south of Germany since 1905. And myself, I'm the CEO of Rentschler Reven, the fourth family generation nowadays. So the seminar today is about industrial air cleaning. So I want to give you some information around the machine tool, about the so-called oil mist, the mist we have inside the machine, around the machine, and of course through our air cleaners. Unfortunately, too often, too much oil mist outside the machine in the manufacturing halls. And for this, I have a lot of useful information for you today in our seminar about industrial air cleaning. First questions we are often asked on our booth: for what reason do I need air cleaning? Of course, the first answer of that is environmental protection for our working people. But for industrial air cleaning can be much more reasons. During the seminar today, I will show you that oil mist separation, industrial air cleaning can have a huge impact on energy costs, on consumption costs. We will later on see some case studies for that. Or it has a very big impact on the lifetime of your coolants. So on the coolant costs, air cleaning can have a huge impact. We made last year a case study in Germany with DMG Mori. The case study was on a huge milling center for long-term milling applications. If you have an air cleaning unit on such a big milling center, the airflow through the cabinet of your machine can again have a huge impact on your workpiece. Keep the temperature much more stable over a long-term milling operation, for example. So air cleaning therefore can even have an impact on your product quality. That you really can participate about from such advantages, you need technology, a good technology for separation and filtration. Furthermore, we need knowledge about the airflow engineering, how to calculate the right airflow for your machine. And last but not least, you should have an intelligent air cleaner to fulfill standards like a modern manufacturing, like Industry 4.0. Also for this, we will show you later on examples. So like I said, we need, for good sophisticated air cleaner, we need a good technology for filtration and separation. What is the definition of technology? For this, a little bit not so serious approach for definition of technology. So why we showing this cartoon? Nowadays there's technology everywhere. So you walk around here, you pick up some leaflets, you read some product description, technology, technology, technology. You go over there in the neighborhood, it's a shopping mall. Even there you can buy fabrics, running shoes, running socks, even running socks, technology inside. So what is the real definition of any kind of technology? I think the definition of technology is a bit more serious and brings it on the point. Technology is the application of scientific knowledge for practical purposes, especially in industry. So, means scientific knowledge. We need knowledge from university. We need knowledge from research and development labs. And this knowledge we transfer from the scientific side to our product. This is real technology. Everything else is maybe a good advertising, but not technology. So in our field of the industrial air cleaning, we started to research and develop on that topic 20 years ago. We started to research what happens inside our machine. What happens when the air goes through an air cleaner? What happens inside here? And of course, what happens around our machine? So what I want to present you today in this seminar is more or less the results of 20 years research and development on the field of industrial air cleaning. So a first very simple topic I want to give you some knowledge about in this seminar is what happens with the airflow in our machine tool. So for example, like you see here in the picture, we have a milling machine. On top of the machine, there sits an air cleaner. So what does this air cleaner do? Of course, he sucks out the so-called oil mist from the machine and tries to clean it, to separate it. But this is the first very important fact you should in future think about when you are talking about industrial air cleaning on machining centers. If you suck out on the top, for example, 700 CFM or 1000 cubic meter per hour, you suck this out on the top. So we need then somewhere an area in our machine where the air can flow back into the machine. Otherwise, you will get a negative pressure in your cabinet. So on a milling machine, it's very common that we can use the chip conveyor for the air coming into our machine. Then we make a lot of studies and analysis what makes the airflow through our machine housing, through the cabinet, where the air goes, how it goes over the spindle to the air cleaner. These are all topics you have to research. This can be very critical on grinding machines, because obvious grinding machines don't have a chip conveyor. They have a very good housing. So often the people not pay attention for this fact that when we want to suck out on the top, we need somewhere on our machine openings where the air can stream back into. So it's a first very important thing you have to consider. So then the next field we worked a long time on is the research and development of the oil mist itself. So what do we have inside such a cabinet? It's some kind of mist, or others call it smoke, or others call it steam, but we have something out of this inside. So it took us a long time to really analyze what it is. So nowadays we call it not anymore oil mist or steam or mist. It's what we are faced to are liquid airborne particles. Inside such housings we have liquid airborne particles. So very similar like a raindrop, just much smaller. So it took us a long time to use particle counters in such environments to really analyze. And through these studies we found out that most of this so-called oil mist are particles in a size range of 10 micron and smaller. So what you see here are examples of different particle sizes compared to a human being's hair in approximately 80 micron diameter. So in the biggest, the largest particles in oil mist, it's usually 10 micron or smaller. So in the books and newspapers, you often read about PM10, like here written. So PM10 is just a spectrum from 10 down to 0. So this is what usually size-wise we are faced with when we are talking about oil mist. And because it is so small, this is also the answer why it's rated quite dangerous. So oil mist, coolant mist, it's size-wise very similar what you have when you have cigarette smoke or cigar smoke. So the particles burning from a cigarette or cigar, it's size-wise very similar to what we have on a oil mist in a machine tool. Good is a first information about what we are faced with when we have to talk about machine tool and oil mist, what we find inside here. And then a next point over the last 20 years was what sucking power, what airflow power, what exhaust volume do I need? 20 years ago there was 4 or 5 airflows coming and this is it, no calculation, no analyze. So nowadays we work with databases and based to airflow exchange rate we can calculate quite simple the needed exhaust volume. So the data for an exhaust, for an air exchange rate per hour is based to the density of the coolants, how much coolant I have in my machine. So if you have an application looking like that, you see it's quite a lot smoke, steam, oil mist we have inside the machine. And in such an example, we work with air exchange rates about 500. This means in 1 hour we have to exchange this volume about 500 times to get this amount of mist under control. The density itself, the concentration of the particles, so how many I have in this cabinet, this can be easily to concentrations up to 500 milligram in 1 cubic meter. So if you're thinking about a cube with 1 meter by 1 meter by 1 meter, inside this cube can be liquid airborne particles in the size range we saw before, up to 500 milligram. If you use this information now together with the fact that we know it's a PM10 spectrum, we already can calculate a lot only with this quite simple data. So to calculate the needed exhaust volume, we need the air exchange rate we used before. Then we need to calculate the workspace, and then we already can find a needed exhaust volume. So in this example, we said the workspace volume is round about 2 cubic meter, and if you calculate this with the needed exhaust air exchange rate, we come to a needed exhaust volume our unit must have. Quite simple calculation, and this it's valid for any kind of machine tool. We make a similar approach. So if you have this data, the air volume together with the concentration, this can give you now an idea how much such an air cleaner can separate in 1 hour. So this concentration multiplied with the exhaust volume gives us half a kilogram, half a kJ liquid per hour. Or make it more simple, it's almost a bottle of whiskey we suck out of the cabinet. Almost in 1 hour, if you have a quite small air cleaner in this size, running at 1,000 cubic meter per hour, the liquid he takes out of your machine together with the air volume can be close to a bottle of whiskey or wine. And then, of course, it's important to keep this liquid in the system and not blow the system to the blow this liquid to the building. So like you see it in the next file on a smaller mudsack milling machine, you see the separator on the top, and the liquid is drained back to the machine, back to the coolant tank. So we keep the liquid, the particles inside the system and not get it to the manufacturing area. So this a first information size-wise and also how much we can have in the air or in our air cleaner. So now I also want to give you some information about the workplace exposure limits. So what we are talking now, it's not anymore inside the machine. Now we're talking what happens around the machine, what happens in our manufacturing plant. For this, these limits are valid. So to make this more understandable for you, I compare these limits to city limits. So inside manufacturing halls, the limits are between 1 to 10 milligram per 1 cubic meter. So the 1 milligram is, for example, a limit coming from automotive industry. A lot of automotive companies have specification which says maximum what we tolerate inside our manufacturing plant is, for example, 1 milligram in 1 cubic meter air where the people are running and working around. If you compare this to city limits, what is accepted downtown London or what is accepted downtown Paris, what we still rate and say it's a good air, this is 50 microgram per cubic meter or 0.05 milligram. So if I take 1 cubic meter city air and I find less than 0.05 particles, also in the size range like we saw before, below 10 micron, this is the limit. What we say in cities, the air is still good. So to make this more clear, I have an example from the downtown Shanghai we took last year also during a machine tool show. This was a day we saw a lot of wind in the city and the wind blow out the smoke and it was nice like you see in the picture. So on this day the air rating was at an index of 40. This 40 means just we have less than or around 40 microgram per cubic meter of the particle like we saw before. Then they say in Shanghai or also downtown London or Paris, the air is good. So just a day later, the sky was same blue, the sun was shining same, but the wind stopped blowing. So it was smog alarm in the city. They didn't allow the kids in the school go out in the break. Most of the people wear masks. And there was an index at 350. There are also a lot of people have applications on the phone and you see index 350, very dangerous for health. But this means just we have in 1 cubic meter air, city air, 0.35 particles PM10. So if you memorize now these figures, 350 or 0.35, and we compare these figures to what is indoors sometimes still accepted, you will see the gap. So this is from a good customer of ours in England called AES Seals. And you see, if we would accept a 1 milligram per cubic meter, this would, in the outside city language, this would be an index 1000. So our target and what we recommend ventilation consultants or plant managers is that our target must be to reach an air quality which is rated outside acceptable. We also have to achieve inside the manufacturing plant. We cannot say outside it's dangerous for the kids and the grandmasters and the insides we accept it for our workers. This makes no sense. So the approach must be reach same qualities which accepted are outside also inside. And that is this possible. You see in this example, So this was a complete project to replace a complete air cleaning concept. And in the end of the day, we reached the air quality with 0.02 milligram inside the plant at AES Seal. And this would be in outside city language an index of 20, which is also outside accepted as no danger for health and people. So I think this gives you a little bit of feeling that these are really not limits where you can say it's still okay when I'm around there. These are super critical maximum limits you can somehow not even or should not accept. So, but with this information, you also got another idea what a real contemporary, modern, good engineer air cleaner have to do. So again, inside we are at 500 milligram or up to 500 milligram per 1 cubic meter concentrations of these particles. This would be in the outside language an index of 500,000. So to come from here to here, this gives you an idea how good the separation and filtration performance have to be of an air cleaner. So, unfortunately, there is not one single system on the market, not even in the laboratories, not even at the universities. There is not one system which can handle all of these different particle sizes, all of these different concentrations. So a real good air cleaner makes a combination out of different technologies. So first of all, you can separate. You can separate with centrifugal systems. Then is another technology, you can make filtration. And then is a third technology, electrostatic filtration, or even with HEPA filter, which comes more from the clean room. And every technology, every system makes sense for different particle sizes. So bigger particles, larger particles can be better separated. Then there are filtration systems we can use, make smaller particles to bigger ones. We can make some kind of agglomeration. And for super small smoke particles, for steam and gas, for example, you also can do some high-efficient filtration with electrostatic systems or with HEPA filters. But for this, again, you have to know. You have to know on my machine which particle size I have, which particles are in my housing. So again, we have to measure. Or like to say in other words, only if you measure, you really know what is going on. So this comes from a very wise guy from Baron Kelvin. Yeah, you have to measure it, otherwise you don't know what's going on inside your machine tool. So how can we measure oil mist? In the end of the day, the principle is the same like particle analyzing in clean rooms. So in hospitals or in Intel chip manufacturing, these are clean rooms. And in clean rooms, you can analyze and measure with particle counter the amount and the size of particles. And the technology for analyze particle sizes in machine tools in oil mist, it's the same. Of course, the environment is a much different one compared to a clean room. And this was quite tricky. So 20 years ago, it was not possible to measure oil mist on a scientific level. But this is an equipment, nowadays it became possible, and this is an equipment you can go to your application. So we take this to big partners of us. This is, for example, an example from Grob in Mindelheim. We take the equipment to the prototype machine, we put on a laboratory unit, and then we can analyze. We can measure how many particles we do have inside. And if I can analyze and know how many, I have to analyze which size. And the size multiplied with the amount gives us the total amount of liquid we have in the air we are faced to. So this is very important. And nowadays with the modern machining, it becomes again quite challenging, because often the oil mist is not oil mist anymore. So why that? Because modern machines with very high RPMs, with a lot of very high coolant pressure, with a very big cutting deeps of the chips, this generates a lot of energy. A lot of energy is often a lot of heat. And if you have a lot of heat, then this can happen. Then you don't have any more liquid airborne particle. Then your particle goes from liquid to gas. It becomes a gas molecule. So the coolant goes to gas. And this can be a problem, because gas molecules cannot be separated. It's just a molecule, so size close to zero, weight close to zero. So if you want to handle a steam molecule, you must first condensate it. So like you see here on this picture, when you suck in steam from here, you can use surrounding air coming into the system here, and this have often a temperature difference, a delta T, from more than 20-30 degrees. This helps us make the opposite thing you just saw before. It brings us the steam back to an airborne particle, because we have condensation. So this example you see better in the next one. This is GKN in north of Spain. They have an industrial washing machine, and inside the washing machine is a very hot 80 degrees steam, and the air cleaner uses the same technology. We suck in the surrounding air, we condensate here to have particles, and then the particles can be separated. So it's a now you see the hot steam coming out. Okay. So what you saw in this example was the steam must be separated. So if we would not have this condensation system before our air cleaner, it would just blow through the steam like in a steam railway. So you first bring it back to particle, then you can handle it. So another example that it needs some knowledge what we are faced to. So if I finally have the particle, then the question, how can I remove this particle from the airflow? How can I filter it? How can I separate it? For this we use an X-cyclone technology. It's a technology awarded 2013 also in Germany for the German Technology Award. So the system for separate sits inside the air cleaner, 90 degrees to the airflow inside here. You see in the next chart, so it's just elements slided in the unit. And the complete airflow have to flow over this system to get separated, like you see in this video animation. Additional can be used spray systems to wash out solid particles. For example, if you have a cast iron application, it makes sense to also have a spray system to wash, to keep the maintenance down at zero. Because not all the time it's a pure, clean liquid particle. Often it's like shown here, it's a mixture of it. It's a mixture of liquid airborne particles together with solid particles. And in a separator, you can handle them with a spray system. So now we go a step deeper. We go inside this element and have a look how the airflow works. So what you see now is the principle there. The airflow with the liquid airborne particles goes inside. Then the airflow goes to a rotation up to 20 meters per second, and the particle cannot follow this rotation and it's thrown out. So what I show you here is, of course, very simplified the real airflow through such a system. The real airflow we started to analyze around about 20 years ago by using CFD systems. So a CFD system stands for computerized fluid dynamics, and this is a technology. One of the first company using that, for example, in the automotive was the McLaren company from England. And they start studying the Formula One chassis, also with the help from CFD systems. So if you have, for example, a look on the front wing of this race car, you see how fragmented, how complicated such a wing really looks. And if you want to understand what makes my airflow here, you need also CFD systems. You have to analyze this with computerized fluid dynamics to really understand what makes my airflow on such complicated systems. And this is what we done also in our oil mist air cleaner. We wanted to really understand the airflow through our systems. So we started to analyze, for example, what you see here, the different colors stays for different particle tracks. So often the people make the mistake in ventilation engineering. They say, okay, now I know what my airflow do. And they say airflow same like particle flow. This is very seldom the same. Very, very seldom a particle takes the same track like the airflow. So this is an example how we study, how we accumulate knowledge around this topic. Finally, I want to give you some interesting additional facts around the topic of air cleaning. So the material, very important. So we recommend not powder-coated steel, we recommend high-grade steel, stainless steel for the housings. So even they are powder-coated, we recommend to use powder-coated because normal steel over centuries, the air cleaner face to the coolants, often the system can look like that. So corrosion is a huge topic. This is why we highly recommend use for the housing stainless steel or at least a high-grade steel which is not sensitive for the corrosion. Another important fact is since 2013 in Europe for fans, so this is how the fan looks inside an air cleaner. The fans have to fulfill an energy standard in Europe. They have to deliver certain efficiency rates. So old fans like this one, it's very compact because the motor sits inside a fan wheel. They are not anymore allowed, or most of them not fulfill this new European guideline. So this new European guideline, which you have to deliver, otherwise you are not allowed to label it CE, says the fan impeller together with motor and electronic control systems all together must deliver certain efficiency rates that you fulfill this new European standard noted here. So this is first, like I said, important that you are CE labeled. And second, it has a huge impact on the running costs, on the consumption costs. So in Europe, if you take an electronic device, doesn't matter if a computer, a light, an air cleaner or a machine, if you take a unit that needs 1 kilowatt, 1000 watt or 1.34 horsepower. And you start this on the 1st of January and let it run 7 days, 3 shifts, and the whole year. So this device with round about 1000 watt will generate you in the end of the year bill in UK round about for 1,000 euro. So very easy to memorize. 1 kilowatt, 7 days, 3 shifts, the whole year generates you a bill in the end of the year for 1,000 euro. And this is even in China or United States nowadays a topic. So energy cheaper in these countries compared to Germany or UK. But even there you have to pay money for your electricity, and it's still 500 euros. So in what dimension this can have, I have you now 2 examples. So one example, our UK director, Sean, did at the AES company here in England. They had before 36 air cleaners with a totally yearly electronic, only electronic, no service, no consumption filter. We're only talking about electronic consumption. So they paid a year 124,000 pounds for this plant you see here. And after modernize, after upgrades the plant, we can reduce the cost to this volume per year. Just 1 year, this different. So time-wise, we cannot go into details, but we have a booth in Hall 5, and Sean and his service teams made this very detailed under LEV standards. So they go from machine to machine. Even in the analyze, they check the day rate is different like the night rate they have to pay. So it was a very, very detailed analyze, and the result of this you saw on the slide before. So there's also under the LEV standards very important to catch the existing airflow, not the airflow in the catalog. A lot of systems are filter systems, and a filter is have a good airflow when it's new, and when it's used it goes down. So Sean goes to the companies and pick under LEV testing the real existing airflow and calculates the specific fan performance. This means the consumption divided by the existing airflow. And if you have a green system, a modern system, fulfill this new standard, saves you a lot of money, you are usually at a value below 1. Another very extreme example from a customer in the north of Spain, in Zumela, GKN Driveline. They make the gear parts there for the automotive industry. They have inside the plant more than 120 air cleaners. The electrical consumption for these air cleaners is 200,000 pounds. 200,000 pounds. They only pay for the electrical consumption. So this is why I really ask you, when you memorize the figure before, so 1,000 watt, 1,000 euro, or a bit less in pound, but anyhow, this is an important figure you can memorize, and often the people you mention this in the first step, they just not believe you. So another last important stuff is Industry 4.0, make the air cleaner a kind of smart, talking with me, talking to the building systems. An example how you can solve that is, this is what unfortunately even nowadays is not an all manufacturer standard. So in some air cleaners you even not see if they have voltage or not. So, but this is not what we call smart. So what we call smart is we have also an airflow device, an airflow sensor showing by optics, by LEDs, if the airflow is okay. So this is a sensor you can put put into the system like you see it here. This is the airflow adjustment with the sensor, and the sensor in big you see in the next picture. This sensor checks online permanently if the airflow is on a certain range. You can set a max and a min value, and then just by a green or red LED it shows okay, not okay. And this signal you also can bring on your building system, or you can also bring on the control unit of the fan. So stuff like this, installation like this, goes a bit into the direction, make also an air cleaner a bit smart and communicating with the building and my machine. A last one, at least, a last important fact, at least for the people working with a neat, pure cutting oil, for example, in the grinding machines, is the flame resistance. So separator air cleaner also can be, sometimes have to be tested against flame resistance. Means a flame, can it go through my separator, my air cleaner or not? And these tests are very, very important in food industries, another business field where we clean the air. In companies like Ferrero, in these units, it's around about 1,000 kilogram of liquid oil. And of course, you can imagine what happens if a spark or something goes through a system like that. Or our British daughter company, Reven UK, is also very, very active in air cleaning in the oil and gas. Every oil rig station drilling for oil have duct separators on it with the same technology, with the same system inside here. And there, of course, flame resistance is also a huge topic. So a flame resistance test is shown here. What you see here is the UL testing. Inside here sits a separator. The whole system have an airflow. And then it's tested if the flame can go through this air cleaning system or not. Like I said, at least where machine industry is working with a pure neat cutting oil, this is also a topic. So this is a manufacturing plant of Volkswagen where they make gear parts. So this is a grinding line where they use water-based coolants. On the other side, you see grinding machines operating with pure neat cutting oil. And you can imagine if in a machine like that they are connected to a centralized ventilation system, if inside a machine like that a fire or explosion would happen, this would be a nightmare for the whole system. Often the fire dampers are used, are not closing 100%. The fire happens, you have a change that the fire jumps through the duct from machine to machine. So that this is not a theoretically analyzed, that this really can happen. We had realized very painful 2006 in January in Germany. So what you see here, a manufacturing plant like this burned completely down to ground. This was a fire 2006 in January at the Walter Tiger Tools close to Stuttgart, happened in a grinding machine. A tool broke, explosion happened, CO2 system killed the fire, CO2 disappeared, and for some reason there was a net with a hot glowing, and the fire restarted, and it goes over the duct from machine to machine. This was, since Second World War, the biggest damage happened in Germany through fire, only because of a topic like you saw before. So fire resistance also can be a topic in combination with air cleaners. Yeah, I'm already 5 minutes in overtime, so just to give you a little bit knowledge, a little bit idea about air cleaning technology, I touched some points. We are also in the Hall 5 with a booth the whole week, so we also can go into more details, and all the units we can show you. We also have a sample and a demonstration like you see running here in the movie. Everything is in the neighbor hall on booth 5, in Hall 5. And yeah, we would like to welcome you. Also can come in the afternoon. We have nice wine here. Thank you.